We have a problem here now, though, because there's really two different types of square roots. There's positive square roots and negative square roots. Let's take the positive square root. So we can write that like this. When we took the square root, that got rid of the squaring on the left-hand side, and we have to take this positive square root of the right-hand side as well. So we're taking the positive square root of 126. If you use your calculator, you'll see that the square root of 126 is 11. I'm rounding off, and again, I'm rounding off without worrying about significant figures. I'm just rounding off to what feels good. So we ended up here with 11. Now this is going to be an answer, so we need to include the sign. Well, this came out to be the positive root, and the units are meters per second. So this is a good answer. The final velocity is positive 11 meters per second. But wait a second, it seems like we should also have to take the negative square root. If we took the negative square root of both sides, what would happen? Well, that would give us now we're taking the negative square root of 126. Now, your calculator is designed to just take positive roots. So when you use the square root on your calculator, it's just going to give you 11. But we can easily see that the negative square root then would be negative 11. If the positive square root is positive 11, the negative square root is negative 11. So we've gotten two different answers. Both of these are good, reasonable answers, and you want to include both of them to really answer the problem. So a full answer is that the final velocity could be positive 11 meters per second or negative 11 meters per second. If you haven't already, why don't you pause the video and try to figure out what this means? What does it mean if our velocity is negative 11 meters per second, and how could that happen? Try to pause the video and give some thought, just a little bit of thought to how this could come up. All right, I hope you have this in your notes now, because I'm going to erase a bunch of stuff to make some more room for myself. Let's go back and think more about the path of this object. So remember that at this point, the object started slowing down. At this point, the object started slowing down, and it started accelerating with a magnitude of 9 meters per second squared. We started accelerating with a magnitude of 9 meters per second squared. Well, let's think about what the path of this object is going to look like. Well, it's going to keep moving to the right, but it's going to be moving slower and slower and slower. So the object is still moving to the right, but it's moving slower and slower and slower. Let me recopy this down here. We're still moving to the right, but we're moving slower and slower and slower, and that's going to continue after we pass the 25 meters. So we're moving to the right. Even after we pass 25 meters, we're going to keep moving to the right. But eventually, we're going to have to stop, right? Because if you keep slowing down, eventually your speed is going to get to 0. So we started moving to the right, but if we keep slowing down, eventually we're not going to be moving to the right anymore. And then what's going to happen if we continue accelerating to the left? Well, if we continue accelerating to the left, then we're finally now going to turn around and start moving to the left. So up here, we're in a position where we're moving to the right and accelerating to the left. That just means that we're slowing down. But eventually, we're going to get to a point where we're not moving anymore, where the velocity is 0. And then if we continue to accelerate to the left, now we're going to be in a position where we're accelerating to the left and moving to the left. The acceleration tells you how the velocity is changing. So if the acceleration keeps pointing to the left, eventually we're going to have to start moving to the left as well. So we're going to move this way and then come to a brief instantaneous halt and then start moving the other way. And now that we're moving this way, are we going to be speeding up or slowing down? Well, notice that now the acceleration is still to the left, but now the velocity is also to the left. Remember that if the acceleration is pointing in the same direction as the velocity, that means you're speeding up. So now at this portion, we're going to be speeding up faster and faster. Maybe I'll make a note of that. In in this portion of the experiment, we were slowing down. Because originally we were moving to the right and accelerating to the left. That means you're slowing down. But eventually you're going to slow down so much that the velocity is 0. And then if you keep accelerating to the left, you're going to have to start moving to the left. And now the acceleration and the velocity are in the same direction, so now we're speeding up and while we're moving to the left. Well, now the acceleration and the velocity are pointing in the same direction. We're moving to the left and then still accelerating to the left, so we'd be speeding up. And this is going to basically continue indefinitely. We're going to keep moving off to the left, going faster and faster and faster if we continue accelerating to the left at 9 meters per second squared. Okay, so now let's think about the total path of the object. Let me show you again more graphically what's happening. So we started here, and we were moving to the right, but we were moving slower and slower and slower and slower until, for an instant, we stopped moving. And then we start moving to the left faster and faster and faster. So again, the chalk indicates the motion. Moving to the right, but slower and slower and slower until, for an instant, we're not really moving at all. And then we continue to accelerate to the left. So now we're speeding up faster and faster and faster. Now, of course, in reality, you'd be moving back along the same path you came across. The only reason I'm putting this path down below this path is just so that they don't obscure each other. So in reality, the chalk is going like this, moving slower and slower and slower and slower to the right, and then moving faster and faster and faster and faster to the left. Slower and slower and slower to the right, and then accelerating faster and faster to the left. So in reality, you would go back along the same path that you set out along because we're doing one-dimensional motion. But I put the return path down here just so we could see it clearly and not confuse it with the outward path. Well, the key thing here then is to notice that there are now 2 places at which your displacement is positive 25 meters from the initial starting point. At this point, we're positive 25 meters from the starting point, and we're moving to the right. But how about when we start going back? Well, then there's going to be another point at which we pass the 25-meter mark, but now we're moving to the left. Now I think hopefully you can start to see why we got 2 different answers here. We're going to pass the 25-meter point twice. We're going to pass it once when we're moving to the right. That's the positive 11 meters per second. And then we're going to pass the 25-meter point again when we're moving to the left. That's the negative 11 meters per second. So both of those are equally good answers, and if you left either of those out, you really would not have given a full answer to the problem. So the question was asking, what is our velocity going to be when our displacement is positive 25 meters? And a full answer would be, well, the first time you pass the 25-meter mark, your velocity is positive 11 meters per second. But when you're coming back along the return path and you pass the 25-meter mark again, now your velocity is going to be negative 11 meters per second. Maybe now you can start to see why we have to be so anxious about paying close attention to the signs, because there's a big difference between positive 11 moving to the right and negative 11 moving to the left. Maybe also now you can see why it's so crucial to clearly mark out what your positive direction is. We chose to the right to be positive, so when we're moving to the left, that's our negative direction. Okay, so now we've seen what to do when you have to take a square root when you're solving a kinematics equation. If you have to take a square root to solve a kinematics equation, you should consider both the positive and the negative square root. Now, there are some problems where one of the square roots doesn't really make sense for the problem that you're working on, and then you can just throw it out. Sometimes one of the square roots won't be appropriate for the problem you're working on, and you can throw it out, and you have to just think about the problem to see when you're in that situation. But you can't just assume going in that you can ignore the negative square root. You have to start by paying attention to both the positive and the negative square root. And in this case, both the positive and the negative square root were quite meaningful. The negative square root gave us some very interesting information that we might have missed otherwise, which is that we were going to pass this 25-meter point twice, once going to the right and once going to the left. Really, if we once you get comfortable with this, you should have noticed that when you originally drew the path. When we originally drew the path, we really should have said to ourselves, well, gee, the path really looks more like this. We're going to pass this once going to the right and then back going to the left. But even if we hadn't noticed that, the math forced us to recognize that.